Hi everyone, and welcome to this video on the Ramsey-Cass-Koopmans Growth Model with both a labor and a leisure choice, right? We will have to modify what we had discussed before in the Ramsey-Cass-Koopmans model to incorporate at least in the way that we sort of discussed before. We're going to incorporate labor hours into the production function, which is basically adding another unit or another input in production, as well as this leisure concept in the utility function, which consumers also derive satisfaction from. So the goal is we will modify the old Ramsey-Cass-Koopmans growth model by altering the utility and production functions. Okay. In particular, okay, people like consumption and leisure, right? So think of like a vacation. It also gives satisfaction to people. And of course, they like consumption. Consumption is the primary driver for happiness, right? And what we do is we let HT be hours worked. Now, people don't really like working in general, so we let HT be hours worked. And for simplicity, we normalize the total hours to 1. So if you think about like, say, 24 hours in a day, well, we can normalize the 24-hour workday as, say, a number 1, and then let HT be the hours work, and 1 minus HT would therefore be leisure. So hence, okay, leisure is 1 minus HT, okay? So the production function is now made up of 2 inputs, capital and labor, right? In this case, labor hours. So we have that YT is equal to F HT KT, right? So as with a normal solo growth model, the production function likely is a function of capital as well as work hours, right? So first thing we do, okay, is the social planner's problem. Is written out as, okay, we want to maximize the value of capital, which is basically maximizing, in which we're choosing how much hours is worked by the representative agent, how much capital they will invest or derive tomorrow over time, right? So this is an infinite horizon problem wherein we have beta t, u, and utility now is a function of both consumption and leisure. So we now have 2 arguments in the utility function. We have consumption and leisure. So we have 2 arguments in this particular utility function. And for notation purposes, we denote consumption as the first argument and leisure as the second argument. Okay, number 1 and number 2. Right, so we now have 2 things that factor into utility. If I consume more, that increases my utility. If I generally get more leisure time, that also increases my utility, right? So if you recall, CT has a particular expression, and that's basically the production. In this case, we now have both labor and capital, so that's HT/KT plus 1 minus delta KT minus KT plus 1, right? And basically, if we know this CT, then we can plug it in. Plugging it in, plugging this in, if we plug this in, we get V K naught is equal to max HT KT plus 1. Okay, sum T is equal to 0 to infinity beta T U F HT KT plus 1 minus delta KT minus KT plus 1. That's the first argument. And the second argument is just 1 minus HT. Right? So again, this entire thing here, that's CT. This one is leisure. Right? So from here, we can derive the Bellman equation. And this will be given as V KT is equal to max. Again, we have two choices, HT and KT plus 1, which is starts with the utility. That's again CT, which is FHT KT plus 1 minus delta KT minus KT plus 1 minus HT. So this is basically like U of C before, but now we have two arguments plus the continuation value of the function beta V KT plus 1. Okay. We have that there. So since we have two decision variables, we will have two conditions. In particular, two FONCs, or two first-order necessary conditions, right? So first things first, we need to derive the function with respect to HT. If we do that, okay, so notice, let me just refresh you. This is CT, right? And this is leisure. We will denote CT again as the first argument, leisure is the second argument, right? So if I derive it with respect to HT, notice HT does appear in this first argument. In particular, it appears here, right? So we have to derive the first argument, which is CT, with respect to HT. So we get U1 CT 1 minus HT, right? Just in shorthand notation, times the derivative of the function with respect to HT, at least on its first argument, which is CT. That's F HT HT KT, right? So we have that. Then notice that HT also appears here, right, in the leisure part. So we need to derive it with respect to its second argument. So plus U2, that's the leisure one, CT 1 minus HT. Then the derivative of that is -1, right? Because 1 minus HT, derivative with respect to HT, that's -1. Then in the continuation, we don't have HT, so that we end there. So this should all be equal to 0, right? Next, we have partial V KT with respect to KT plus 1. So this one would be equal to, notice that we only have KT plus 1 in the first argument, right? And the continuation value. So we only have U1 CT 1 minus HT times, if I derive with respect to KT plus 1, that's -1 plus beta. Then I derive that value function, that continuation value with respect to KT plus 1, V KT plus 1 times KT plus 1, as a function of KT plus 1 rather, is going to be equal to 0. Okay, therefore, we have that, okay, if I transpose this to the other side, that takes out the negative. If I transpose this to the other side, that takes out the negative. I get U1 CT 1 minus HT times FHT HT KT is equal to U2 CT 1 minus HT, right? And I also have that U1 CT 1 minus HT is equal to beta V, expected value, right? Because we don't know this particular thing. Beta expected value V KT plus 1 KT plus 1, right? So we have those two equations. Let's label it 1 and 2, right? So next, we need an envelope equation, again, because we do not know this derivative explicitly. So we can get, using the envelope theorem, we can get first the derivative of the value function with respect to KT and bring it up a period. So next, we derive the envelope equation. So if we derive the envelope equation, we get that if we derive it, so we need partial V KT with respect to KT. This would be equal to U. We're going to derive it. So notice we only have KT in the first argument, which is CT. So that's U1 CT 1 minus HT times the derivative of the function inside. So that's F of KT, HT, KT. Then we also have plus 1 minus delta. Plus 1 minus delta. Right? So that's what we have there. Okay. Then all we need, okay, is, so if this is the derivative, we bring this up 1 period forward. So this is again equal to VKT KT. What we need is VKT plus 1 KT plus 1, right? So VKT plus 1 KT plus 1 is equal to U1 CT plus 1 1 minus HT plus 1 FKT plus 1 HT plus 1 KT plus 1 plus 1 minus delta, right? So we have, good. Then we have this one. Now we can plug it into 2. So plug back into 2. Okay. So we get that U1 CT 1 minus HT is equal to beta expected value of U1 CT plus 1 1 minus HT plus 1 times FKT plus 1 HT plus 1 KT plus 1 plus 1 minus delta, right? So we have those there. That's our new equation 2, right? And for just to recall ourselves or refresh ourselves, let's just copy equation 1. Equation 1 is what we derived when we derived with respect to ht. So copy, and let's just paste it over here. Okay. Now equation 2 again has a special name. Okay, we call this this particular equation is our Euler equation, right? Euler equation, basically that. Okay. So what about equation 1? Well, equation 1 tells us some story. Okay, tells us something. So if I just rearrange it, right? Say I have equation 1, which is u1 ct 1 minus ht f ht ht kt equal to u2 ct 1 minus ht. If I divide both sides by u1 ct 1 minus ht, this cancels out. I get that fht ht kt is equal to 1 minus ht is equal to this ratio, which is u2 divided by u1. And in fact, this is what we know as the ratio of two marginal utilities, which in fact is just MRS, right? So equation 1 tells us that the MRS between consumption and leisure, right, is equal to the marginal product of labor. So this is a key point that this equation 1 is telling us, at least in this model, right? So we have that there. Now, as we did before, we appeal to the steady state, or we say something about the steady state. So at the steady state, so again, we have these two equations here. Let me just copy it so that we can say something about it. So we have these two equations here. Then what we have in these two equations is if we manipulate 1, we find that, okay, at the steady state, again, all of the variables now will be time invariant. So we get u1 c star 1 minus h star f h star h star k star is equal to u2 c star 1 minus h star, right? Right? So we have that one there. So that again yields us basically our old condition, which is if you divide it by u1 c star 1 minus h star, u1 c star 1 minus h star, we get the same conclusion that the marginal product of labor is equal to the MRS between consumption and leisure. But a more interesting result that we can get is when we manipulate equation 2. So if we manipulate 2, we find that, okay, so 2 is given as u1. So again, all of these will now be in the steady state. So c star 1 minus h star is going to be equal to beta expected value u1 c star 1 minus h star times f k star h star k star plus 1 minus delta, right? Then notice, again, we really don't need the expectation because at the steady state, it's time invariant. What we can do is we can divide both sides, okay, by this U1 term, U1 C star 1 minus H star, U1 C star 1 minus H star, cancel, 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 cancel. I'm left with 1 is equal to beta F K star H star K star plus 1 minus delta. If I divide both sides by beta, I get 1 over beta is equal to F K star H star K star plus 1 minus delta. Then I transpose this term to the other side. I get 1 over beta minus 1 plus delta is equal to Fk star H star K star. Then recall, okay, recall beta is equal to 1 over 1 plus rho, meaning 1 over beta is just going to be equal to 1 plus rho minus 1 plus delta, the 1s will cancel out, is equal to Fk star H star K star. Then we find that the marginal product of capital H star K star is equal to rho plus delta, right? Is equal to rho plus delta. Very similar to what we find in the normal Ramsey-Cass-Koopmans model. So we have now two particular equations that we derive that are quite interesting. Marginal product of labor is equal to the MRS, and the marginal product of capital being equal to rho plus delta, okay, in this case. Okay, so that's it for this video in being able to use or at least derive a dynamic programming problem with both labor and leisure components in the model. In the next video, we will put an explicit functional form and continue on with how this can be derived in a specific functional form. So thank you for your attention, and I'll see you in the next video. Thank you very much.